Hello everyone, welcome back to the Computer Networks lectures. In this video, we'll be talking about the connection management in TCP. But before we start, let us recall what we have studied in the chapter 2. As we all know, the client and server that runs applications that runs over the TCP protocols, such as HTTP, SMTP, and so on, before they can start the communications, they have to establish the TCP connections so that they can exchange messages, right? And not only that, after the communication has been done, they have to close the TCP connection. So we will be talking about those two things: how to establish TCP connections and how to close the TCP connections. All right. So in these slides, okay. So before we start about the handshaking or the establishing TCP connections, there are two main important, let's say, goals in the handshake. The first one is to agree to establish connections for both parties, client and servers. Okay, and then the second one is to agree on the connection parameters, which is on the initial sequence numbers. As we know that in the TCP, we need to have the sequence numbers to track down the order of the bytes that they are being sent by the senders. Okay, now let us start with the illustration of two-way handshake. Okay, we can take the example of the human communications. Let's say Alice wants to talk to Bob. And then first Alice can initiate the communication with the some introduction, asking Bob to talk. So you can say let's talk, and then Bob replies with okay. And then similarly in the computer networks, let's say the client can initiate the communication with the request connection message and choosing X as the initial sequence number, and then the server can reply with accept connection with the X as the initial sequence number. So after the request connection message is received by the server, the communication can be established at the server side, and after the reply from the server is received by the client, then the connection at the client side is also can be established. But the question is this two-way handshake can work in the networks? Okay, as we know that there can be variable delays, as we have already studied in the retransmission scenario, there can be a pre-method delay that makes for example, the accept connection message arrives a bit late, and then after the timeout in the client already reached, so the client might retransmit the request connection message. Right? Uh, it can be due to the variable delays, or it can be due to the message loss. Okay, so there will be some message ordering issues, and then the issue here is that if we are only using two-way or two-way handshakes, uh, especially the server cannot see how whether the client has already received the accept connection message. So let's take a look at the two-way handshake scenarios, several scenarios, and I'm suggesting you to read the RFC 793 that contains the standard for TCP protocol. Okay, so let's have a look at this three scenarios in two-way handshake. The first scenario is the ideal one, where the client sends the request connection message to the server accepts it, and then send back the accept connection message to the client, and then now the communication can be established, and the client can start to send the data by using the let's say incremented sequence number, and then the server replies with acknowledgement until they finish the communication. So this is the ideal case, and there's no problem with that. Now in the second scenario, let's say the request connection message is sent by the client and then received by the server, and the server sends the accept connection message. But then there is delay when the server sends this accept connection message, so that the timeout is already reached in the client. So the client sends another request connection message. But anyhow, since the client, I mean, it receives the accept connection message anyway, so the client uh, assumes that the connection can be established, and then they can start communication, and then after sometimes they close the communication. But then, as the client didn't know that actually this accept connection message is delayed, being delayed, so actually it retransmits the request connection messages. Okay, and then it is received by the server, and the server, since the server does not initiate its own sequence number, so it just receives the transmitted request connection as just some normal request connection message. So it replies with the accept connection message, and then the connection that was already closed can be reestablished. I mean, this is something that is not shouldn't be happening. Okay, uh, we'll see in the three-way handshakes this can be prevented because both sides, the client and server, they have initiated they are giving out the initial sequence numbers, so they can track the current states of both sides, in the client and in the server. Okay, this is also called the half open connections, and again, I suggest you to read the RFC 793 to get more information about the half open connections. Okay, this can happen in two-way handshake scenarios, but this can be prevented in three-way handshake scenarios. Now, uh, the third scenario, this is actually just an extension of the second scenario. Again, the same case, the accept connection message is delayed from the server to reach the client, and the client already sent out another retransmitted the request connection message to the server, but after the request connection message is transmitted, eventually the accept connection message arrives, and both client and server can establish communication, and then the client can start to send data, right? Okay, now if we go back a little bit, since the client transmitted the request connection message, and the same way as the previous scenario, the second scenario, the server send back a reply, accept connection message, and then again the client has to retransmit the data, the same data. Again, this is because the server does not give the initial sequence number. So in this case, there is a problem of duplicate data accepted by the server. All right, so now let's take a look at the three-way handshake scenario. Now we have states in the client and the server state. As we know in the socket programming, the state of the server is always listening to the incoming socket request or socket connection by the client. In the beginning, client also in the listen state. So when it wants to communicate with the server, it start by sending what's called a SYN message, TCP SYN message. Why is it called? Why this is called SYN? Because in one of the TCP flag, we have to set the SYN bit to 1. Okay, so this means that the client wants to initiate TCP connection. Okay, and then another thing that is important is the client initiates the sequence number, let's say with X. This is just a random number. It can be 1, 0, or something else. Okay, so upon receiving this TCP SYN message from the client, okay, so before that, okay, when the client sends this TCP SYN message, the client is in the SYN send state, and upon receiving this SYN message from the client, the server state is in the SYN receive state. Okay, so after that, um, the server has to send acknowledgement from the TCP SYN message sent by the client, and then the acknowledgement, we set the acknowledgement bit to 1. Okay, and then the acknowledgement number is equals to x plus 1. Because let's say this is just one byte, so the next transmission, the server expects the client to send sequence number with x plus 1. And another thing is that the server, so this is just to acknowledge the SYN bit, the SYN message from the client. And the most important thing is that the server also agrees, if the server agrees to the TCP connection establishment by the client, it sends the SYN message also from the server, where it sets the SYN bits to 1. And also it initiates the sequence number from the server. Let's say the initial sequence number from the server is y. So it can be same between x and y, but then we assume that y is also a random number. Okay, now upon receiving this SYN ACK, so we call this message, this one is called SYN. Okay, and then the reply from the server, we also call it SYN ACK, because actually the server sends SYN message with the ACK message. So the ACK message is piggyback in the SYN message. We also call it SYN ACK. So after the client receives the SYN ACK message from the server, the communication from the client side can be established. So basically, the client can start sending data, but it's not done yet. Now the client has to acknowledge that it receives the SYN ACK sent by the server by sending a message with the ACK bit set to 1, and the acknowledgement number equals 1 plus y plus 1. Now we have the server states also established. So now at this point, both server and client can start perform some message exchanges. Okay, this is the human three-way handshake protocol. I'm going to skip this one. I'm just go straight to the closing TCP connection. All right, so when the client wants to close the TCP connections, the client can send a TCP message with the flag fin set to 1. Okay, so fin also stands for finish, if I'm not mistaken. So as basically, if just remember this thing, if the client wants to start the TCP connection, it sends the SYN message. But the client wants to close the TCP connections, it sends the fin message. Now the server has to respond the fin message sent by the client. On receiving fin, the server can send the acknowledgement. So this is a normal way to do. Okay, and then to totally or to completely close the TCP connection, the server has to send another fin message to the client. Then the client has to also reply with the acknowledgement. But then the same way as what we have seen in the TCP connection establishment, the server can combine the ACK with the fin. Okay, so the server can send fin ACK message in response to the fin message sent by the client. Okay, so simultaneous fin exchange can be handled. So okay, let's take a look at the flow diagram here. So if the client wants to close its TCP connection, it sends the fin message to the server. The sequence number can be X, or it's just the last sequence number that is sent by the client. It's different X from what we have seen in the TCP SYN. Okay. So the client state at this point is the fin wait 1. So basically, at this point, the client is waiting for the fin message sent by the server. Okay. And also at this point, the client can no longer send data, but it can still receive data because it still expects the fin message from the server. Okay, now after the server receives the FIN message from the client, it sends the acknowledgement, okay, with acknowledgement number x plus 1. In this At this point, the server state becomes closed wait. Okay, after receiving the FIN message from the client, and after the server sends the acknowledgement, the server can still send data. Okay, because it is not still not closing the connection with the client. And again, upon receiving this acknowledgement from the server, now the client state still in the fin wait. So if it was fin wait 1, now it is fin wait 2 because still waiting for the server to close the connection. Now finally, the server sends fin message to the client, and then when the fin message is sent by the server can no longer send data. All right, and then uh, it will wait for the last act sent by the client, and the client state becomes time wait because it takes some time before it really closes the TCP connection with the server. And finally, upon receiving the FIN message from the server, the client sends acknowledgement. So upon receiving the acknowledgement from the client, the server state is now closed, completely closed, while the state in the client it has to wait for 2 times maximum segment lifetime. Okay, so it is a bit longer than the segment of the normal segment lifetime. So this is completely closed the TCP connection in both client and the server. So I think this is it for the TCP connection management. We'll continue our lecture with the TCP connection control in the next video. So see you then in the next video.